Hello everyone, I'm Hao. I'm going to present our work EMO, which is a real-time emotion recognition system for eyewear. This is a joint work of Nanjing University, Microsoft Research, and Kitware. The first question is what's eyewear? Eyewear is wearable devices for eyes, such as augmented reality, virtual reality, and eye trackers. These devices paint a magical future for HCI. Eye wearable devices have brought some powerful applications to the field of education, commerce, entertainment, and healthcare. Emotion recognition is highly desirable for eyewear. It can improve service quality to make the eyewear more intelligent. For example, when it's detected that the user is curious about some knowledge, more content can be introduced. According to the user's likes and dislikes, optimize the recommended goods. Adjust the difficulty of the game according to the user's emotions. Emotion monitoring can also be used for mental treatment, such as depression treatment. This work studies how to recognize user emotions on eyewear devices. EMO uses single-eye images recorded by the eye tracking cameras to identify the 7 most common human emotions, such as surprise, anger, and so on. We propose 3 techniques to realize emotion recognition. The first technique we proposed is to effectively extract emotional features from single-eye images. The second technique is to perform fine-grained personalized classification on the extracted features. The third is to make full use of the data locality and recognize emotions in real time on resources limited eyewear. Emotion recognition of single-eye images on the device faces 3 challenges. First, it's hard to extract features from single-eye images compared to the whole face case. Second, different people express the same emotion in different ways. Third, the device resources are limited for real-time computing. Next, I will introduce these problems in detail and explain how we solve these problems. These are images used for emotion recognition in the whole face case. As we can see, there are many facial changes and muscle movements to indicate emotions. For example, all muscles of the nose, mouth, and forehead can be captured. The following images are the single-eye images recorded by the eye tracking cameras. Features are quite light. Only the muscles around the eyes and the part of the eyebrows can be recorded. Fortunately, psychological research indicates that the emotional features around the eye account for 65% of the whole face, and eye tracking cameras can always capture a close view of fixed area. This provides us with feasibility to recognize emotions based on single-eye images. To meet the challenge, we designed a CNN-based extractor. This extractor is an improved retinite, which is friendly to single-eye images. Since it's hard to obtain a large number of eye area images to train the feature extractor, we adopted a transfer learning. Transfer learning is a research problem in machine learning that focuses on storing knowledge gained while solving one problem and applying it to a different but related problem. For example, the knowledge gained while learning to recognize cars could apply when trying to recognize trucks. Transfer learning can solve the problem of insufficient dataset during training. We can also borrow this idea during training the feature extractor Please note that the dataset used for fine-tuning and the data collected by EMO are the same in the image content, but there are still slight differences in the data. This difference may exist in real scenarios, because the model may not be able to obtain information during use when training. However, due to our feature extractor's excellent performance, the experiment proves that the fine-tuned model on the corrupted data shows the excellent performance in actual use. Recall that since different users express different emotions in different ways, we designed a personalized classifier to realize emotion recognition. Please note that this personalized classifier is appended to the feature extractor when it is used. It takes the output of the feature extractor as input, and then classifies the features extracted by feature extractor into 7 categories. Below, I will introduce it in detail. These are eye-aware images of different users when expressing the same emotion. We can say that these muscles' movements and changes are quite different. Different users express the same emotion more differently than the same user expresses two different emotions. Therefore, a one-size-fits-all classification strategy cannot meet the requirements. To meet this challenge, EMO has designed a personalized classifier. The algorithm and hyperparameters of personalized classifier are pre-trained, and then the classifier will be deployed into the EMO system. When the system is first used, the classifier will determine the parameters according to the characters of the user's emotion expression. That is, the user needs to do some initialization the first time the usage. Users first record their emotions. The system will perform feature extraction on their emotions, remove outliers, and then calculate the reference point and the intra-class distance. The system will record reference points and distance for different emotions. Initialization can be done in a few seconds, and it only needs to be performed once. In the following use, feature extraction will be performed under single-eye images, and the personalized classifier will classify the emotion with extracted features. We just use the feature extractor and personalized classifier to complete the single-eye images-based emotion recognition. But the procedure is very expensive, and the inference latency is very high. This is not acceptable on resources-limited eyewear. Therefore, we have optimized the system to achieve real-time recognition. The core idea of optimization is to make full use of the locality of the emotional data. Next, I will introduce this in detail. I will start by introducing the necessary for real-time emotion recognition. This is a series of images recorded by the eye tracking cameras when the user expresses surprise. The frame rate is 25. As we can see, the emotion surprise lasted only 22 frames, which is about 800 milliseconds. Without real-time detection, emotion surprise may be missed, or the user's feedback may be inconsistent with the content on the screen, such as when a user with AR shopping goods, he may be recommended a disliked goods, expresses the disgust, and then continues to browse other goods. If the recognition is not timely, the disgust tag may be wrongly labeled to other goods, which will lead to a false recommendation preference. Through the analysis of the emotion recognition scenario on the eye wearable devices, we found that the locality in the emotional data can help us optimize system performance. By fully considering the locality, we designed two components to realize real-time recognition, namely the frame sampler and the fast forwarder. The insight behind the frame sampler is that After changing emotion, there will be a pause. The insight behind the fast forwarder is that the images within the same category are highly similar. Let's take a look at how these two components work before we go into the details. Please recall that we already have a personalized classifier that can complete emotion recognition with feature extractors. First, the current frame is labeled by the personalized classifier. Once the emotion changes is detected, the frame sampler will be notified to immediately label some of the next frames. Then the fast forwarder will calculate the similarity between the current frame and the frame when the emotion changes. If the similarity is high enough, the current frame will be labeled immediately, and then the frame sampler will start to label the next few frames. The procedure will be repeated until the similarity between the two frames is low, and then it will be handed over to the personalized classifier to label the frame. The frame sampler is a heuristic algorithm that labels data according to the feedback of the fast forwarder and the personalized classifier. The fast forwarder is a semi-SNET-based metric learning model. Metric learning aims at automatically constructing task-specific distance metrics in a machine learning manner. What we see here is the architecture consists of the feature extractor, personalized classifier, and the frame sampler. Please recall that the feature extractor is a deep CNN network. Here, we will divide it into two parts. Please note that the extractor is naturally layered. We do not make any structural changes. We only want to use the features produced by its middle layer, which is the high-level semantics features of the input. Next, the fast forwarder takes the features here as input, judges the similarity to the previous character expression. If the similarity is high, it immediately outputs the label. If the similarity is low, it continues to compute the remaining feature extraction and personalize the classification. Next, I will introduce the high-level workflow of the system, the prototype, and the evaluation results. Let's review the key components of EMO following the system's workflow. The eye tracking camera first records the Eyewear video, and then the frame sampler will determine whether the current frame will be labeled as the emotion just detected. If it cannot be labeled, the frame will be delivered to the feature extractor to extract the high-level features, and the forwarder will determine the similarity with the previous frame based on the immediate features. If the similarity is high, the frame will be labeled. Otherwise, the feature extraction will continue, and the personalized classifier will perform classification on the extracted features. This is the prototype we built. There is a helmet, a dial board, a portable battery, and an infrared camera. This is the collected single-eye image. We conducted a comprehensive evaluation of both recognition and system performance. In 7 emotion recognition, the accuracy of the system is up to 76.6%, which is 1.8 times the baseline. The processing speed is 20.9 times the baseline. The usage of CPU, memory, power, and storage are all lower than the existing work. Now, let's summarize this work. We have designed an emotion recognition system for eyewear devices. There are 3 features. First, EMO works on the single-eye images. Second, there is a personalized classifier to deal with the differences in the emotional expression of different users. Third, the system can run in real time on resources-limited devices. We believe that this system can also provide a design reference for other intelligent video processing services. Specifically, how to design personalized intelligent services, and how to optimize intelligent system performance. Thank you for your attention. Any questions?